Okay, I want to begin with this so that we go back to some of the theory of what's going on to explain what's happening. And I'm going to explain the world according to Jim. So view this as a working hypothesis, not a cast-in-stone theory. I believe that the expression of CAM photosynthesis is a drought adaptation response. I believe that the expansion of C4 photosynthesis is related to low CO2. Now, I have chosen my words carefully. I'm not saying the evolution of this is a result of that. I'm saying the expansion, so that natural selection might allow many things to persist, but natural selection by change in the environment might favor the expansion of one group over the other. Okay? And so what I'm suggesting is that C4 photosynthesis expanded as a result of a decrease in CO2 concentration. Karina, I'm not saying it was 600 ppm or 400 ppm, but what I'm suggesting is that at some point, the Earth crossed a threshold, and the CO2 concentrations got low enough that the C4 pathway was more advantageous in some places than the C3 pathway. So that's the foundation of what I'm going to show you for a bit. One second. Because I need to explain time and space variations. Chris, question.
Does that coincide with our best graphs of changing CO2 concentration globally?
Chris asks, does this expansion associate with our models of CO2? And the answer is yes and no, but you need to know the literature. It's no if you believe some colleagues like Mark Pagani or Kate Freeman, when they first came out with their studies, that made certain assumptions about fractionation factors with microbes that were their biomarkers. It's yes if you now believe that some of those data are no longer applicable. So it's very clear that CO2 decrease and C4 expansion occurred at about the same time, but they may not be at the same time within a million years. They might be at the same time within 5 to 10. Lena.
That expression for in all the places on Earth, or you start in a particular...
So that's what we'll talk about. I need to explain why C4 photosynthesis expanded, and I need to explain why it expanded first in the warm parts of the planet and then in the cold parts. Was there another question? How old is the fossil record for C4? About 20 million years. Yeah, probably 20, maybe 25. I think it keeps getting pushed back. But there is evidence. So what is my evidence? It's going to be a fossil. Okay. In some cases, I might be able to get a carbon isotope ratio, but for sure it'll be a fossil. So what's going to drive this? What's going to drive this is a very simple biochemistry. I told you that in C3 plants, CO2 combines with a 5-carbon molecule to form 2 3-carbon molecules. I only told you part of the story. It turns out that this enzyme Rubisco, which grabs onto a CO2 molecule slowly and converts and then does this reaction, can also catalyze a second reaction. It can catalyze a second reaction in which oxygen comes in at the same time. And if oxygen comes in at the same time, we get 1 PGA, phosphoglyceric, and we get 1 PG, phosphoglycolate. So we get a 3 and a 2. And along the way, we end up having CO2 spinning off. And in biology, any process that evolves CO2 is called respiration. people noticed in the 70s that there was this unexplained respiration that had nothing to do with mitochondria. And because it occurred only during the light, they adopted the term photorespiration. So it's CO2 evolution that takes place during the light, but they didn't know anything about it. They thought it was some pathway here or there. They just didn't know until George Bose made this incredible observation in the early 70s that this enzyme rubisco would grab onto a CO2 molecule, as everybody knew, but it would also grab onto an oxygen. And the ratio of those two reactions followed very predictable Michaelis-Menten competition kinetics. What does that mean? It means it's the ratio of CO2 in the environment to the ratio of oxygen. Chris?
Can you comment on the Koch effect?
No. We'll save that for later, because that's pretty complicated. So the observation here is that fundamentally an enzyme is going to be able to take two substrates, and its ratio is going to depend, or its activity is going to depend on the ratio. Now, we accept that for the most part, the CO2 concentration of our planet has changed over time. But the oxygen concentration hasn't changed, or not changed very much. So what you see is variation in photorespiration reflecting the history of CO2 concentration in our planet in C3 plants. And C4 photosynthesis becomes an an evolution, a feature, such that the CO2 concentration around the enzyme doesn't fluctuate, stays very high at 1,500 to 2,000 ppm. So I like to say that in modern plants, C3 plants, they tend to be CO2 starved. In C4 plants, they enjoy the CO2 environment of the good old days, where the CO2 concentration was 1,500 to 2,500 ppm. Because it's important for you guys to remember, this is how plants photosynthesize. Everything diffuses in, right? There's no tidal volume like you have in animal systems. Because you don't have a tidal volume, when the CO2 concentration on the outside gets low, CO2 concentration on the inside is low. So how do I get to the good old days? I use the C4 pump system. Now I can show this mechanically in this graph here. This graph says, well, what's it like today at 400 ppm CO2, and what's it like in the good old days at 2,000 ppm CO2? And what you do is you crank through the cycle 10 times, 10 CO2 molecules come in, and you see that in the system that has no photorespiration, you get 10 carbons fixed. In the C3 system, you get 7. So there's a 30% loss of efficiency in C4 photosynthesis in today's environment. If we go to the glacial periods, when CO2 concentration was 180 to 200 ppm, it was more. C4 plants really don't care what the CO2 concentration is. They've got this concentrating mechanism. C3 plants are very much responding to that. So that becomes the basis of why we might expect C3 and C4 plants to occur. And now I need to explain something else first. And that is that not only can the enzyme take up CO2 and oxygen, that is rubisco, but it's temperature sensitive. And it relaxes at higher temperatures and becomes more receptive to oxygen. So we have more photorespiration potential at higher temperatures, and we can draw a plot here of concentration and temperature and the ratio of photosynthesis to photorespiration, and see that, man, you get into low CO2 environments that are hot, it's bad news. That creates an opening. That becomes the advantage place for C4 photosynthesis. Warm environments, low CO2 environments. Okay? Now, you need to be a little practical, and I have to tell you, I have gotten into extensive arguments with a number of my geological colleagues. They say, Well, we go to these warm environments and we don't find any C4 plants. What's going on? You can't be right. And I'll say, Billy, fictitious name, pick on the man. Billy, you got to be reasonable. I'm talking about warm environments where plants are growing. I'm not talking about Death Valley in the middle of summer when there's absolutely nothing growing. So if you go to any warm environment where plants are growing, I'm going to predict you will have C4 photosynthesis. But you take away water and you don't see it. And I'll give you the analogy that you'll see most of the time. If I go look at the grasses in San Diego, they're C3 because the plants grow during the cool season. There's no rain in the summer. If I take that same latitude, go to the east coast of the United States, to Orlando, all the grasses are C4 because it's the same temperature, it's the same latitude, but now you have rainfall. So you've got to have water in order for what I'm saying to occur. Now, this is sort of fundamentally obvious to a biologist, but I realize that it's not always so fundamentally obvious to everybody because it's the temperature in which the plants are growing. So now let's tell you that we can use carbon isotope ratios because Rubisco discriminates, but PEP carboxylase does not. Yeah. Maria, yes.
So you expect to have more C3 plants when you go higher in altitude and latitude?
If higher latitude is colder, the answer will be yes, and you'll see that. So I'm going to get into those examples now, because I need to explain why we should have C4 plants and why they should show a very predictable spatial pattern. So I'm going to use carbon isotope ratio, because PEP carboxylase doesn't discriminate very much. And so we can think about this in theory very quickly with Sean. What's the carbon isotope ratio of the atmosphere? Minus 8. What's the diffusion fractionation? 4.4. So I'm going to expect most C4 plants to be minus 8, minus 4.4, about minus 12. Okay? Because those are the two effects. C3 plants, I'm going to expect them to be minus 8, minus the B3 factor of 27. It's not fully expressed. I'm going to expect them to be in the negative 20s. And in fact, that's the variation you see. So let's now go into applying this. You say, well, Jim, you gave me the equation for C3 photosynthesis. Give me the same equation for C4. And I'm going to tell you that the isotope effects are additive. So I need to take the CO2 molecule and ask what's the fractionation from CO2 in air to CO2 in water. I know that CO2 isn't the active component, it's bicarbonate. What's the fractionation from CO2 in water to bicarbonate? I know that there's a fractionation during the carboxylase reaction. What's the fractionation between bicarbonate and C4 material? So that's adding up the elements in the top equation. And when I do the equation, and to reduce it, I get the equation on the right. And that equation on the right is almost identical to the equation for C3 photosynthesis, except it has a B4 factor, which we didn't have in the other. We had a B3. And it has a B3 times theta. Otherwise, it's the same. So the important thing here to recognize is what is theta? And theta is the leakiness. And that takes into consideration something which is pretty obvious once you begin to think about the physics. If there was no theta, then it would be B4 plus B3 minus 8. But if there was no theta, the B3 value would be 0. Theta represents the incorporation of a CO2 molecule that got decarboxylated. It's in the bundle sheath cell and says, heck no, I'm not going to hang around, and it diffuses back out. it leaks back out from the bundle sheath cell into the mesophyll cell. Of course, it's going to get refixed and come back in. But that leakiness is captured by the term theta. And it turns out there are phylogenetic and environmental variations in leakiness. So that under drought, you can get variation in C4 plants because of a change in leakiness. We won't talk about that in this class. Chris?
We've talked a lot about diffusion versus active transport, like when we were talking about roots and how we once thought it was diffusion and now aquaporins seem to be a major key player. Is there any evidence to suggest that diffusion is alone acting here, or is there evidence to suggest a possibility of other circuit codes?
So this represents our current interpretation. I think the literature has established that there are aquaporins in all systems. It is now established that there are aquaporins that facilitate gas diffusion. So we know now, I was just going to mention very quickly, that there are aquaporins that might facilitate CO2. So could some of this leakiness be attributed to an aquaporin sensitivity? It could. I think it is way too early. But right now, the current hypothesis and the supporting data are to suggest that there's some sort of a physical leakage. That could change in 5 years. This is a very active area of research. 2 years ago, I would never have told you that CO2 diffused into the chloroplast using aquaporins. I didn't even know until a year and a half or 2 years ago that anyone had described an aquaporin that was a CO2 channel. So it's not that CO2 can't diffuse through a lipid bilayer, but its diffusion is facilitated through that. And so now that gets into a discussion you and I had yesterday about terms such as mesophyll conductance and so forth. And we attribute it to one thing versus another. The challenge is that they become very difficult for us to measure. So I'm not going to talk about mesophyll conductance, but I do want to make you guys aware that there is an emerging literature that suggests that aquaporins transport water or conduits or channels for water, and that they may actually be channels for CO2. And that opens up all sorts of exciting opportunities. Because if I can engineer these pips, I can do a lot. So stay tuned. So this is a repeat of what I'd shown before. In C4 plants, we have the spatial separation of the PEP carboxylases, and in CAM, we have a temporal separation of those activities. And what that means then is that this is the isotope ratio equation for CAM plants. And so you might say, gee, Jim, that implies that there's very little, if any, variation in CAM plants. And the observation is, yes, there's much less variation. But there is variation because CAM plants can actually play a funny game. CAM plants can occasionally decide that early in the afternoon they're going to turn into C3 plants, and they open their stomates. They haven't turned on the PEP carboxylase, but they're expressing some C3 photosynthesis. So instead of keeping the stomates totally closed during the day, they might open them up at 4 o'clock in the afternoon. And if they open them up at 4 o'clock in the afternoon, and RUB carboxylase is still active, then they're going to be expressing C3 photosynthesis. And the extent to which that happens can give you variation in the isotope ratios. True CAM plants that never change their isotope ratio show very little variation. They're about -12. But you'll see values to -14, -16 as some C3 photosynthesis gets expressed. Okay. Rather than allow you to ask questions, I am a sweet and low fan. I use sweet and low to the detriment of myself, probably. But I grabbed a bunch of these alternative sugars and measured their isotope ratios. I want you to talk to your neighbor, and then I want you to tell me which sample here is a fake. Okay, just talk to yourself for a second. I want to know what sample here is a fake. So which of these, let's go through these one at a time. Organic cane sugar in the top right. Cane, is that a C3 or a C4 plant? C4. So we accept that isotope ratio? Good. Okay, sweet and low, minus 11.2. What is sweet and low? Sweet and low is saccharin. Saccharin. Sure. You can take sucrose and glucose and convert it into saccharin. That's fine. Splenda. Oh, it's probably some sort of a something or another, but it's made from a C4 plant. Apriva. Well, I can't tell you what Apriva is.
Yeah, what is it? I think
Well, it says something. It describes a sugar, but it's not a C3 or it's not a C4. That's not the fake. The fake is stevia.
Oh, because stevia comes from C3.
C3 plant. So stevia is a sweetener 1,000 times more sweet than sugar. I looked it up last night, and it was a C3 plant. Okay, explain to me, Emily, how do I get a C4 isotope ratio in a C3 plant? You can't. It's a fake. What is it? Well, I'd have to do the molecular analysis. I don't know what it is. But it can't be a synthetic. They claim that this comes from a plant. Yeah. Now, I have no idea what the word organic means, but I want to tell you, that's a fake. I don't know what it is. It'd be a subject of a good chemistry test, but it is not stevia, unless they have discovered the world's first stevia C4 plant. And all the literature I have looked at says that stevia is C3. So, okay.